Right, back so soon, and that is because life is just so exciting. I said yesterday I might get out after the video I compiled yesterday and see the partial lunar eclipse. So when it got a little bit dark, the sun had gone down and the eclipse was at its maximum, I went out into the garden and tried to find the moon, but there was no sign of it. So I flashed up my astronomical program, and that told me that the moon was very low on the horizon and not visible from my location. So I had to get the camera and make it off up not a massive hill, but it's a bit of a distance away. So I went out there and I did, in fact, despite the low cloud or thin cloud, I did see the partial lunar eclipse, and I've took some photographs of that, and I'm going to show those at the end of this brief explanation, because I think viewing the event is very exciting, but understanding what you're looking at is in a way even more exciting. And I'm not pretending to be an expert on astronomy. In fact, far from it. Astronomy gives me a serious headache, but it's very exciting. So I've fathomed out, or tried to fathom out, what's actually going on, and I'm going to try and explain it to you. We on the Earth are orbiting the Sun, and we'll take that orange ball to my left as the Sun and this tennis ball as the Earth. So we go around the Sun, and it takes us approximately 1 year to do that, and we do so in a plane called the ecliptic. So if you can imagine this spirit level attached to the sun there, and just been wound round and going round and round and round in that plane, and we travel around the sun in about a year. And while we're doing that, the moon, represented by this golf ball, is also orbiting around the Earth, but its orbital plane is slightly inclined to the ecliptic plane that we orbit the Sun. Now, as the moon goes round the Earth, half of the moon is always illuminated. One hemisphere is illuminated by the sun, just as one hemisphere of the Earth is illuminated by the sun. But we can not always see all of that illuminated hemisphere. When the moon is in this location, and it'll be usually either a bit above or a bit below the Earth, because its plane is inclined at about 5 degrees. So when it's here, we'll see a full moon. We'll see the full illuminated hemisphere. When it's progressed round to there, we won't see the illuminated hemisphere at all. So that'll be your new moon. I'm not sure which direction it goes round in, I'm not sure. But it'll go from new, and the phase will increase until you eventually get a fully illuminated moon, and then it'll decrease back to new again. And that happens, the full cycle takes about 29.5 days. So hopefully that explains the phases of the moon, and hopefully it explains why you don't get a solar eclipse on every new moon and a lunar eclipse on every full moon, because it doesn't, the planes are not lined up, but they do occasionally intersect. And if they happen to intersect when the moon is in one of these two locations, either behind the Earth or in front of the Earth, then you'll get an eclipse. In front you'll get a solar eclipse, as the moon blocks out the sun's light reaching the Earth, and when it's behind you'll get a lunar eclipse, when the Earth's shadow is stopping the light from falling on the moon. Right, but slightly more complicated than that, because obviously the Earth is much bigger than the Moon, and the Moon is also much smaller than the Sun. But as it happens, the Moon is about 400 times smaller in angular diameter, but it's also the Sun is also about 400 times further away. So it just so happens that in space, from our perspective, the Moon looks almost the same size in the sky as the Sun. Now I realise I'm waffling on a lot here, and you might not be interested in the physics, not to mention the mathematics of it all. But it is interesting if you can see something and you can actually understand what's going on. And in last night's case, what was going on was we passed in front of the Sun, between the Sun and the Moon, and the shadow from the Earth was cast onto the Moon. So if this is the Sun here and this is the Earth here, that's the Moon there. But the Sun has diameter in the sky, so you actually get two shadows. And if you were stood on the Moon, as I've drawn this as a total eclipse, a total lunar eclipse. So the Earth's shadow is big enough to actually completely stop any of the Sun's direct light from hitting the Moon in a total lunar eclipse. And if you're in that shadow, that's called the umbra, the umbra shadow. The penumbra shadow is when only part of the Earth's shadow blocking out the whole sunlight is on the Moon. And let's just stick with the total eclipse at the moment, because you get these occasions where you see the blood red moon, the moon will turn red, and that's because even when we are directly blocking out the Sun's light from hitting the Moon, the Earth has an atmosphere, and that atmosphere acts like a lens, but it doesn't lens all light equally. And in fact, the Earth's atmosphere is very good at scattering blue light, and that's why the sky looks blue. So the blue light gets preferentially scattered and the red light gets preferentially lensed onto the face of the Moon, and that's why in a total lunar eclipse you get a red moon, and that red can vary depending on what sort of atmosphere the light's going through. And obviously the other wavelengths will get, the greens and the yellows, they'll get refracted slightly differently, but it's predominantly the reds and the blues that you know, explain what's going on. So last night then we had the Moon passing partially through the umbra shadow of the Earth, so it wasn't totally red, but I've done some exposures at different levels so that it does show that the parts that were in umbral shadow, and only at its maximum 65% of it was in umbral shadow, you can see that area if I overexpose the penumbral parts of the shadow. It brings out the red. Now you might be getting bored by this stage. I know, I realise astronomy makes my head hurt, so it's probably making your head hurt at this point in time. So what I'll do now is I'll just run a few short photographs that I took of the Moon in partial eclipse. So it was in part umbral shadow and the rest of it was in penumbral shadow. But what you've got to bear in mind when you're seeing these photographs is I took photographs at various exposures. So where you've got the Moon here, the whole Moon here, and say part of it will be in umbral shadow, So let's just say that this is in the umbral shadow, so that's very dark. That's where no direct sunlight's reaching the moon. Some direct sunlight will be reaching this part of the moon. So to some extent it looks like a moon with a phase. Although if you knew a bit about astronomy, you'd realise from your location the moon's been tilted the wrong way around or something. But you can see that in this area here it'll be red. In fact, I've done it the wrong way around, it was red at the top. But so let's just say in this area here then it would be red, and in this area here it would be very, very bright or overexposed to bring out the red. But if I correctly expose this area, then this would just be black and you wouldn't see it at all. So there's a lot of different exposures going on in this series of photographs, so sometimes it's difficult if you don't know how the photographs were taken to figure out what's going on and what you're actually looking at. But hopefully, you know, if you went through this, if you want to understand more, then go to some proper astronomy sites. But it's what's going on up above us which is as equally important as what's going on around us. So I just thought it was incredibly exciting, and I just wanted to show you it. And I'm sorry if I bored you, but we'll go straight now into the photographs.